The directions say to sketch the region enclosed by the given curves and find the area. In example 1, the curves are given by the equations y equals 12 minus x squared and y equals x squared minus 6. They're both parabolas, and y equals 12 minus x squared is sketched in blue. Y equals x squared minus 6 is sketched in black. And notice how I drew a representative rectangle within the region for which I want to find the area. Why? Because that rectangle will help me to determine the top function and the bottom function. So the top function y sub t is equal to 12 minus x squared. The bottom function y sub b is equal to x squared minus 6. Now what I want to do is determine the values of x that will produce the same y value. So in other words, I need to determine these points of intersection right here. And so to accomplish that goal, what I want to do is set 12 minus x squared equal to x squared minus 6, which says 2x squared equals 18. Dividing both sides by 2, I get x squared equals 9. Therefore, x is plus or minus 3. And solving for x helps us to determine the limits of integration for my integral. So the area is equal to the integral from negative 3 to 3 of the top function 12 minus x squared minus the bottom function x squared minus 6 dx. So notice again, 12 minus x squared is my top function. My bottom function is x squared minus 6. And I'm going to integrate that difference with respect to x. So distributing the negative inside, we get the integral from negative 3 to 3 of 12 minus x squared plus 6 dx, which is equal to the integral from negative 3 to 3 of 18 minus 2x squared dx. Now, this is 18x minus 2/3 x cubed evaluated from negative 3 to 3. If I replace x with 3, I get 18 times 3 minus 2/3 times 3 to the third. Then I'm going to go minus and then replace x with negative 3. And when I replace x with negative 3, I get 18 times negative 3 minus 2/3 times negative 3 to the third. And then when I do that calculation, I claim you should come up with 72. And that's how we do example 1. Let's take a look at example 2. Suppose we have the curves y equals the square root of x minus 1 and x minus y equals 1. And notice when x minus y equals 1, we can say y equals x minus 1. So notice how the line y equals x minus 1 is sketched in blue, and then y equals square root of x minus 1 is sketched in black. And if you notice, if I draw a representative rectangle, that helps me to determine the top function and the bottom function. So the top function y sub t, I claim, is equal to the square root of x minus 1. The bottom function y sub b is equal to x minus 1. And so what I want to do from there is determine the values of x that will produce the same y value. So in other words, I need to find these points of intersection right here. Okay? And so what I do is I set x minus 1 equal to the square root of x minus 1. Square both sides, I get x minus 1 to the second equals x minus 1. And I'll show you what I do. So I let a be x minus 1. And when I do that, that tells me a squared equals a. Subtracting a on both sides, I get a squared minus a equals 0. Factor out the a, I get a times a minus 1 is 0. So a is 0 or a is 1. But remember that a is equal to x minus 1. Just point of emphasis right here. So I'm going to replace a with x minus 1. And so x minus 1 is 0 or it's 1. Solving for x, I get x equals 1 or x equals 2. And that will determine my limits of integration for that area. So the area is the integral from 1 to 2 of the square root of x minus 1 minus the quantity x minus 1 dx. And remember, we're taking the top function, we're subtracting the bottom function, and we're going to integrate that difference with respect to x. Next page. So this is 2/3 times x minus 1 to the 3 halves minus 1/2 of x minus 1 to the second, evaluated from 1 to 2. Applying the fundamental theorem, if I replace x with 2, I get 2/3 times 1 minus 1/2 times 1. And then I'm going to go minus. Then I replace x with 1, and I get 2/3 times 0 minus 1/2 times 0, which is equal to 2/3 minus 1/2 right here, which is equal to 1/6. And that right there is example 2. Let's take a look at example 3. Now, notice here x is defined as a function of y for both curves. So I have x equals 2y squared and x equals 4 plus y squared. Now, instead of drawing vertical rectangles, we're going to draw horizontal rectangles, because in this problem, we're going to integrate with respect to y this time. And by the way, x equals 4 plus y squared is right here in blue. Okay. Now, from the rectangle, okay, this horizontal rectangle, that's going to determine the rightmost function and the leftmost function. So the rightmost function, x sub r, is equal to 4 plus y squared. The leftmost function, x sub l, is equal to 2y squared. Now, what do we do from here? We need to determine the values of y that will produce the same x. So in other words, we need these points of intersection right here. We need the values of y that produce the same x to get our limits of integration. That's the purpose. It's to get those limits of integration to calculate area. So over here, we set 2y squared equal to 4 plus y squared. That says y squared equals 4. So y equals plus or minus 2. So the area is equal to the integral from negative 2 to 2 of the rightmost function, 4 plus y squared. So this is x sub r minus the leftmost function, 2y squared. X sub l is right here. Now, simplifying, this is equal to the integral from negative 2 to 2 of 4 minus y squared dy. So again, we're taking the integral from negative 2 to 2 of 4 plus y squared minus 2y squared dy. And then we're rewriting this as the integral from negative 2 to 2 of 4 minus y squared dy. Okay. So going further, we get 4y minus 1/3 y cubed, evaluated from negative 2 to 2. If I replace y with 2, I get 8 minus 8/3. Then I go minus, and then replace y with -2 and get -8 plus 8/3. And if I distribute the negative inside, I get 16 minus 16/3, which is equal to 32/3. On example 4, we have the curves y equals cosine x and y equals 1 minus cosine x. Okay, and notice how x is greater than or equal to 0 and less than or equal to pi. Now, y equals 1 minus cosine x is in blue, and y equals cosine x is in black. And pi over 2 lands in the middle, so why do I have that? Because cosine of pi over 2 is 0. So when x is pi over 2, cosine of pi over 2 is 0, so y is 0. And then when I look at this graph here, y equals 1 minus cosine x, when x is pi over 2, y ends up being 1, which means you're up here. Now, we have two different rectangles floating around because here's x equals pi. So we have two regions. One of them's here, okay? And one of them's here, okay? And it's tricky because the top function and the bottom function end up changing. Now, we need this point of intersection right here because at this point, that's where the top function and bottom function change. So let's figure out what that is. So what I'm going to do is set 1 minus cosine x equal to cosine x. That says cosine x equals 1/2, and so x equals pi over 3, right? Now, if you notice, and I'm going to erase just a little bit of this, I have a representative rectangle right here. Okay. And over here, I'm going to erase just a little bit, or a little bit more than a little bit. And I'm going to draw a representative rectangle over here. So notice that my top function and bottom function did change. So on the interval 0 to pi over 3, I claim my top function is cosine x. So in other words, y sub t is cosine x, and y sub b is 1 minus cosine x. On the interval pi over 3 to pi, it turns out that my top function is 1 minus cosine x, and my bottom function, y sub b, is cosine x. So I'm calculating essentially two different areas. Now, a sub 1 is the integral from 0 to pi over 3 of cosine x, that's my top function, minus the quantity 1 minus cosine x. So again, that 1 minus cosine x is my bottom function. I'm integrating that difference with respect to x. So in other words, I'm taking the integral from 0 to pi over 3 of cosine x minus the quantity 1 minus cosine x dx. Now, if I distribute the negative inside and simplify, that's the integral from 0 to pi over 3 of 2 cosine x minus 1 dx. So this is 2 sine x minus x evaluated from 0 to pi over 3. And when we're all said and done, it looks like we get square root of 3 minus pi over 3. So notice I just replace x with pi over 3. And then if I replace x with 0, that's just 0 anyway. And then when you subtract, you end up with square root of 3 minus pi over 3. Now, a sub 2 is the integral from pi over 3 to pi of 1 minus cosine x. Now again, on that interval, that's my top function. My bottom function is cosine x. So this is the integral from pi over 3 to pi of 1 minus cosine x dx. So this is the integral from pi over 3 to pi of 1 minus 2 cosine x dx. So this is x minus 2 sine x evaluated from pi over 3 to pi. And then when I plug in, I get pi minus 2 sine pi minus the quantity pi over 3 minus 2 sine of pi over 3. And if I go further, remember sine of pi is 0. And so this is pi minus pi over 3, distributing that negative, plus 2 times square root of 3 over 2. The 2's cancel, and we get 2 pi over 3 plus the square root of 3. If I put everything together to get the total area, now let's go back for a sec. So notice how I have the area here in blue. So I'm taking the area of this region, and then I'm taking the area of this region over here in red. And basically what I'm doing is I'm adding them together to get the total area. And I had to break it up because the top function and bottom function changed from region 1 to region 2. Okay? And if we go back, let's go back to that last page. So the area is a sub 1 plus a sub 2, which is square root of 3 minus pi over 3 plus 2 pi over 3 plus the square root of 3. Add them up, we get pi over 3 plus 2 times the square root of 3. Okay, that'll do it for this video. This is on sketching a region and finding the area between two curves. Okay, thank you.